All right. Hi, can everyone hear me? All good? All right. So this is our second week of ML Mondays. Today we're going to actually get into the real machine learning part of this, tabular machine learning. It shouldn't be too crazy. This is basically going to be just a pretty brief math light introduction to some of the simpler versions of machine learning. So if you weren't here last week, first of all, my name is Ryan, and I'm going to be doing most of these presentations. Last week we did a bit of Python last week. This week we're going to go tackle machine learning, and next we're going to do computer vision. As obviously you can see a bit more going down the list. Week 8, I'm leaving a little bit vague for now in case there is interest for something specific that we don't have listed on here yet. So if you have any thoughts on that, especially when we get closer, let me know if you can. I'm on the Discord. So today, basically what we're going to be doing is going over the fundamentals of machine learning, at least at a relatively basic level. So for that basically means what is machine learning, because that's not a guarantee. It's sometimes a bit of a nebulous definition, so it's important to go over. Distinguishing what tabular machine learning is relative to the many other options that are out there, as well as several different approaches to this tabular machine learning. After this, we're going to have a quick workshop on a data set concerning the Titanic. Oh, before we go any further, if anyone has any questions at any point, feel free to raise your hand. I will get to you as soon as I possibly can. Don't feel discouraged about asking questions. That's the whole point of this. All right, so machine learning. If you do a Google search for machine learning, you will find many different definitions that don't quite sync up sometimes. The definition that I found that's the most consistent is something along the lines, this is a paraphrase, but any computer algorithm that enables the machine to perform a task without it being explicitly coded for. So for instance, if you're trying to train a machine to, say, predict, I don't know, how many people are going to get an A on a certain test, for instance. They might not, it wouldn't be machine learning if you explicitly coded a bunch of if-else statements and just added the increment or something, because it is explicitly coded for. But machine learning, there's a lot more, there's a bit less explicit. And you could basically have it create its own behavior, which is kind of cool. I will note that that is not the same definition as artificial intelligence. Basically, what AI is a more general term that corresponds to basic computer algorithms that display some form of human-like or intelligent behavior. Ignore the fact that those two things don't necessarily correspond to the same thing. But ML is a part of AI, just as deep learning, which we'll eventually get into, is a subfield of machine learning. Does anyone have any questions on that? 3, 2, 1. All right, I'll move on. So getting more precise for today, tabular machine learning, it's real simple. Basically just, it concerns a table of information. So for instance, imagine you have a Excel spreadsheet or Google Sheets or whatever you use. That is basically what the input is going to be like. So it's generally one of the simpler forms of machine learning. Input is a row of some data table or just a bunch of rows of a data table. So something like this. And the output is generally some form of prediction or some kind of recommendation about the information that you've given it. Within this, there are two overarching things, classification and regression. Out of curiosity, does anyone know what these two things are? All right, I mean, that's why you're here, I guess. Classification, basically, is just a matter of separating a bunch of different instances into a few specific classes that we're looking for. So for instance, if you have, taking an example outside of tabular machine learning, imagine you have some kind of agent where there's like a bunch of pictures and they're all either cats or dogs, you could make a classification algorithm to determine which of these pictures are cats and which of them are dogs. Regression is a little bit different. Instead of doing a specific number, classifying in a specific set number of instances, regression is predicting some kind of continuous value. So for instance, trying to predict what's the next, like the stock of something, some stock, I don't know, let's say Amazon, whatever, in a couple weeks. That'd be really hard. But if you were to do that, that would be a regression task because you're predicting some kind of continuous value that can't be classified. Any questions on this? All right, I'll move on. So I just mentioned now what regression is. I'll do this. What is generally one of the first things taught in machine learning? Pretty simple form of machine learning. It's called linear regression. As you could probably guess by the name, it's linear and it's regression. Very complicated, I know. Basically, through various math, depending on what the actual code you end up using can vary on this. There's a few different approaches, but the main idea is you attempt to draw a straight line that predicts some kind of quantity based on known values. So in this case, I chose a kind of a bad example because it's not as well labeled, but imagine, let's just say there are this many TVs that some like settlement or something has, and you're trying to get sales on a particular item, maybe based on commercials that are being sent. If there's more TVs that show that commercial, you could assume that there's going to be more sales, but the exact amount could be, or at least approximation of which could be figured out via linear regression. Now, what I just showed you is a really simple example where there was literally just one input, one output. That's really simple. Generally speaking, it's a bit more complicated than that because you could have a lot more features. So imagine there's like an arbitrary number of features. The line is going to take something along the form of this. It is going to be a line. It's just going to have many dimensions to it. So for instance, it could be a 3D or 4D line. And when you get beyond 3D, it's a little hard to visualize, but conceptually, it's not too difficult to notice. It's pretty simple, basically. It's just a line, but there's just what you're actually trying to figure out are these beta values. These are coefficients that are estimated by the algorithm, which they can, that is basically your output. You're trying to basically train a model to get to the point where you have good coefficients that give you a pretty good, or at least reasonably good accuracy, because for basically all data sets besides a few very specific ones, you can't hit a perfect one. Generally speaking, this is outside of linear regression. If you ever get like a 100% accuracy, you should be really suspicious about your methods because it shouldn't happen, not usually. Just as general thought. Now, in terms of how we actually get a good line, I'm going to ignore some of like the deeper math because that's generally basically just a bunch of derivative related things or things of gradient descent that can vary a bit, and I don't want to go too deeply into that because we don't have that much time. So I'm just going to simply go after, we're trying to minimize RSS, which is just the residual sum of squares. It's basically just, for instance, this point right here, it is about this far off from our prediction line. If we were to square the distance of every single point from the line, that'd be our residual sum of squares. So obviously, if your line's not a great predictor, it's going to have a higher value, and it's going to, it's not like linear. So if there's certain points that are, a point that's especially far away is going to have an overall larger impact. Any questions about linear regression so far? Nope. Okay. Brief tangent. I'm going to also get into something called logistic regression. It is a little bit weird because it's generally used for, it's kind of used for classification, which is kind of going against what I said earlier. It's still technically regression because what it does is it predicts a probability of some event happening, some value between 0 and 1. Now, due to some math that I don't want to get into right now because it's kind of a pain, but basically, linear regression doesn't really play nicely with this type of thing just because of how probability works. So instead, we use a similar thing in the form of logistic regression. So it's going to have some kind of formula like this, and it'll look like this. So you'll see on one side, this is like a particularly nice data set because it basically predicts it almost perfectly with the exception of a few outlier cases. But just one side is going to be it happens, and the other cases it doesn't. This is how you generally do it for some kind of probability. Something else that I'm going to cover that generally isn't covered that much at the basic level, but it's still like nice to know about, is something called a support vector machine. First of all, I'm assuming has anyone heard of a support vector machine just in passing? Okay, I mean some people mention it a bit. The reason that people sometimes mention this is that before neural nets were a thing, these were basically the best thing we had when it came to prediction. So don't get too worried about the naming here. A support vector in this case is basically just a point that is really close to a line. So the whole point of this is, you see on this visual, we have this big margin right here that separates both prediction classes. The goal of this is basically to make a predictor that maximizes this margin as much as possible. So that way it is most resistant to potential issues that could happen in the future. Getting back to what I was saying before, a support vector is basically the points that are right on the margin and are what determine its size. Now, what I showed you before was basically a linear support vector machine. So like this line. And that works in this case. It's a pretty neat data set, but imagine a data set where it is a lot more complicated, like that it has that, like, for instance, let's say a blue point's like here, like right in the middle of everything, and it just kind of sorted out in a certain way that makes a line like not feasible. So it's either like sort of linear or it's like just totally some weird pattern that you can't easily do. Again, I will not be going into this deeply because the math's actually kind of annoying for this, but just know that there is something called the kernel trick. It basically allows you to do non-linear support vector machines, which you would normally normally take forever to do, but there are ways to kind of shortcut it and make this actually feasible. So for instance, you could have a kernel that looks kind of like this, kind of like a weird kernel that has it's like an exponential type kernel. RBF, I think, is what's generally defaulted to on sklearn, which is something I'm going to get to in a minute. But for instance, you could have a setup where it's not linear. It's clearly there's like bubbles all over the place. Like this one's like totally distinct from this. And as I said before, these were the best performing machine learning algorithm before neural nets. And we're kind of that way by necessity because neural nets, even now they take a long time, but they used to be much worse. And there used to be some issues that we weren't able to really get around until more recently. So I've been mentioning neural nets a bit. I'm not going to be going into them completely in this session because honestly, I could do a whole thing on neural nets on their own. But the most basic neural net that can exist is something called a perceptron. So this is a perceptron. Basically, the graph looks a little weird, but it's basically just doing a weighted sum. That's basically what it's doing. So it takes a bunch of numerical inputs. So let's just say there's like 0, 1, 2, and so in the inputs. And the weights are some value that at the beginning, they're just something random. You basically just multiply, do a weighted sum, and then you apply some sort of activation function to shift it to a certain range. That range is pretty important. I put a bunch of activation functions here. The most simple one would be linear, which is basically not doing anything to it. And that'll work for like the basic stuff, like for linear. It just works well for some kind of linear classification task. But whenever there's a pattern more complicated, it becomes a little bit hairier and it doesn't always work. Generally speaking, what? I'm sorry, I thought I heard a question. Oh, sorry, I just want to make sure. Basically, there's a few other functions as well. ReLU in particular is used a lot in most neural nets as you go forward. I should probably explain what a neural net actually is so you guys have some idea. if you want to take a picture, do that now. Okay. So, who here has heard of a neural network before? Before this lecture, obviously. Okay. Who knows what a neural network is? Okay, I'll try to clean up a little bit. The most basic form of neural network is pretty easy to explain. This is basically what they look like to some extent, at least the basic ones. I mean, there's some that have weirder layers to them, but this is the basic one. So there are all these nodes on the neural net. You see that there's different layers, right? And in this case, there is one connection between each node and between each node and the layer. So the node up there connects to every node in layer 1. This is what's known as a dense layer, and it's the most basic type of layer. As I said before, with like a perceptron, there are basically weighted sums. So they're basically weighted sums going from the inputs to each of these outputs, which are hidden layers. Activation functions are applied, and those values are propagated forward and forward and forward until we get to an output layer, which we get what we want. They'll actually learn. Again, I'm not going to go into it too much right now, but there's a process called backpropagation, which allows us to actually learn from errors on this. You can basically go back and calculate derivatives and such, but I'm not going to go into that right now. You don't really need to know exactly how the math works in order to get how it works, understand how to use it. If you are interested, that's great. You can always look it up. I'm not going to teach that right now. But that's effectively what a neural network is. Does anyone have any questions on that? Question on that. All right. This isn't a super long workshop, so I'm sorry, not a super long presentation, so I'm going to go into the next thing. This is a bit of a quick thing concerning a data set to do something a bit more practical. So could anyone who can go into this QR code for me? You should get to a Collab notebook. I don't think you'll be able to actually edit it, and I don't want you to edit it. I just need you to make some copy of it. So let me know. Let me know when you guys are done with the QR code, and I'll actually go to the Collab myself. Right. Okay, I'm going to go to the next thing. Does anyone still need the QR code? All right. So you should see something like this when you get to the QR code. For you specifically, you probably want to go to File and save a copy in Drive and GitHub somewhere. No, sorry, actually. Save a copy to the Drive should work. So you just get a copy. The reason you're doing that is so that way you don't all edit the same thing, and it would be pretty messy. So once I verify everyone's able to make a copy, we can go on to actually going through this. And hopefully we'll have some time. This didn't take super long. We'll get the experiment with some different things that we haven't necessarily gone over yet. So what is this data set? Let's go to this link and find out. So this is a pretty well-known data set. It describes a bunch of different features of individuals that were on the Titanic and whether they survived or not. So for instance, there's obviously survival, 0 for no, 1 for yes. That's pretty straightforward. You need some kind of measuring stick here. There's ticket class. So this is kind of like for instance, a first class ticket is going to be for someone who got a more expensive ticket, who someone has a nicer accommodations. That can matter. The sex of the person on there would matter, and so on and so forth. Some of these matter a bit more than others, but the point is, basically, it's a nice, relatively clean data set that we can kind of mess with. I've already kind of set it up for you guys on here, so when you look at the chance, you have to. This is offered by me. This is safe. But basically, first we need to import a bunch of modules. You'll notice that most of these are for something called sklearn, which is a pretty nice Python module for doing some of the more simple forms of machine learning. It's a nice one to experiment with if you have time. But now I've already made a copy of this data set on my own, I've basically hosted it via GitHub. So you guys don't have to go through the process of getting it onto here and getting it working. So this shouldn't be much of an issue. And then we can call DotHead to actually see what this looks like. So we'll see. It adds this extra span here, but basically there's passenger ID, survive, which is really important, B class, and a bunch of other features. If you have any questions about the specific features on the Kaggle thing I linked, it actually shows specifically what all these things actually mean. Just because something like Parch, for instance, doesn't. Yes, I guess I'll start with you and then if you.
Yeah, I was going to say, I think your Collab looks a little different than the one that was shared. I don't know if this is mine.
What does it look like? Okay. Okay.
It doesn't have all that info.
Okay. Do you mind if I see what you see? Do you mind if I see it? Interesting. Okay, then, if you don't mind, I need to make a quick fix. I must have put a QR code for something that wasn't being shared before, so a bit of technical difficulties. I'll get that fixed in a moment. In the meantime, just bear with me. Okay, when you get a chance, can you guys check out this new QR code? It should work. If not, I'll have to figure something else out.
Yeah, that one's good.
Cool.
It's not working.
Is it not loading correctly, or is it just going to the same place?
Sorry.
It's good. Is anyone having any issues with this QR code? All right, I guess we'll continue. Sorry for the momentary hiccup, but it looks like it got resolved, so it shouldn't be too much of an issue. As I said before, you should make a copy if you haven't already. Just going to File, save a copy in Drive, and you should get to a screen like what I see. But yeah, just continuing what I was doing. So just run a couple cells real quick. One of the nice things about Collab is that you can kind of choose the order in which you do this. It can be presented a lot more cleanly than just a normal code. You can even put pictures and stuff in, which I didn't do in this context, but Collab's a nice way of kind of showing your code off. So I would recommend using it for at least this type of thing. It doesn't work for everything, but it's nice for this type of thing. But this is a bit of a snapshot of what our data set looks like. I think the actual number of rows is close to something along the lines of 800. But it only shows the first 5 because obviously that's kind of a lot. So first of all, do you think that all of these features are going to be important? Okay, why is that?
The ticket number and stuff is not that important.
So what, for instance?
The ticket number stuff.
I didn't hear what you said by number. Do you mean passenger ID, for instance?
The ticket ID.
Oh, ticket. That one's also not important. So it might not, in the ticket in this case, you have to think about where this data is coming from. So it's a little arbitrary because as you've implied already, if everyone has a unique ticket number, then you're not really gaining anything out of it. It's the same reason that passenger ID is also worthless. Name could potentially be useful if we were to do a lot more processing to it, but we're going to skip that for now. And in that case, because you could go along and say, hey, if it says Mrs. or Lord or something like that, it might affect survival rates in some context. But we're going to skip that now for simplicity. I'm also removing cabin partially because it's a it's a bit dirtier. You can see that there's a bunch of NANs, so there's not always cabins. And it seems to, when I did a check, I think there's at most 4 of the same cabin at one place. You would have to do some processing to make it work. So we are ignoring that as well. So to actually remove that from our data set, we can just call drop and just remove these features right here, because we've already established they're not going to be particularly useful for us. So just in case there are any issues, we also have to make sure our data set is clean. So for instance, we can't really have, our models can't really work with like an infinity or an NAN somewhere. It was not applicable. It's not going to really work. Or it has some kind of data that just straight up doesn't make sense. There are a number of ways of doing that. So the easiest way, not always the best way, but the easiest way is to just drop all rows that have NA in them. So I already have that here, but that might not work in some contexts, because you could have, for instance, you could just have a value like age that's mistyped, and it could say like 300, which obviously is a bit weird. You could like more manually clean it and say if it's like 5 times higher than the next highest age, you might remove it because it's a bit weird. But in this case, we're going to, for simplicity, we are just going to remove all NAs, which if we have already moved cabin won't be too much from what I know. But generally speaking, you want to make sure the data is a bit clean. One other thing that's not amazing about that we do with this data set is that not all of the features, even among the ones we kept, are numerical. So for instance, sex is male or female. Our model, at least our model, can't really handle a string in there. We would need some kind of number. So what we would actually have to do, and it'd be the same for embarked, SCS, that's not going to work for us. So we need to map that to some numbers. And the simplest way of doing that, in this case, it's pretty easy because there's not that many cases. So we just change it so that every female value is just changed to 1, every male value changes to 0, and then we just basically just align these with some numbers. So that way it can be run. This isn't perfect. Depending on how you encode data, sometimes there could be some biases towards certain things. This isn't perfect. This is a relatively safe and fast way of approaching it. But if you were to look more into different encoding processes, if you've ever heard of one-shot encoding, that's one of the ways you could maybe make this a bit cleaner. But for now, we will ignore that. So I'm just gonna run those things. One other thing that's good to note is to know if maybe we could extract the more important parts of our data out and basically give our model a bit of a head start. So just imagine if you were learning some kind of model. It's generally easier if you were given some kind of hint. So for instance, if you were to read the Kaggle thing, you would know that SIB refers to the number of siblings that you have on that were on Titanic along with you, as well as parts, which is the number of parents along with you. So you could kind of make it a bit faster and just get a family size attribute by just getting all siblings, all parents, plus 1 for you. You could also just make something called is alone, which is just going to be, are you the only one? Or do you have people with you? And you can make a new one for is alone. So in our specific example, we're going to just remove basically part, SIB, and family size, because they're a bit arbitrary if you already have is alone. Unless, I guess if you were to look a bit more closely, or if you look at family size, maybe you'll find something. But again, for simplicity, we'll just stick with is alone. So if I were to update this, you'll see that it's a bit simpler now. This is all numeric data, not a ton of features. This is good for what we're trying to do. Because if you have like a bunch of features, it could mess up your program a bit. It could distract from what's actually the actual most meaningful things, because there might be a feature that just doesn't matter, and it could distract from more important things. Any questions, thoughts, issues with what we've gone over so far?
I have a question.
Yes.
So I know like right now you're giving like, for the sake of the workshop, you're telling us like, hey, this is important and this data isn't that important.
Right.
If you were tackling this as like how it's set on the Kaggle like as a competition and you didn't know it.
If you didn't know anything.
do you observe data? Do you use like different techniques to?
So there are some things you could do. I'm not gonna get it all on here, but for instance, let me see if I can actually show you, because there's some like more in-depth versions on here that I could show you. But basically, there are a bunch of modules they can use to kind of just visualize the data. So for instance, you can see, hey, is there a correlation between age and survival? And you can potentially use that to determine right away if there's even something worth looking for with age, for instance. So like if it was just a flat line as it was increased as for survival rates as age is increasing, maybe you don't want to use age. I know that's not the case in this instance because I've already looked at it, but generally there are, you want to actually immerse yourself in the data a bit. I want to see if I can get an actual, yeah, I just want to show you because this person went through really in depth. So I want to show you. I guess so. This is a more simple version. So this is basically real quick. That is basically looking into SIB, so number of siblings as well as whether they survived or not, and basically needs some metrics on there. So when there is one sibling, the survival rate is about 53%. If you go do that in aggregate, you can find some things out. So you can kind of already see that survival rate for high numbers of siblings is a bit low comparatively. So like if you go from, I think once you go to 3 and onward, it just becomes less and less likely. So that's something to observe. It's a way to basically generate some features or remove something. I think in here it even goes over how to extract some useful information from the name, which I'm ignoring, but you could like actually scan for, say, board and figure something out from there. Did I answer your question, or do you think? Okay, I just wanted to make sure because it's hard for me to know. So continuing. So this is a very abbreviated version of how to basically set up our code, basically understand our data, and clean it up a bit before we actually start applying things to it. So we're on to using ML. So we're splitting this up into two things, X and Y. X is our inputs, Y is our output. We care about the survive feature, so we're removing survive from X and we're only using survive for Y because otherwise it'd be obviously if you survived, it's a lot more likely that you survived. It's obvious. It's just like X equals X. It's not useful. So you want to split that up, and there is a pretty useful function. It won't work in every case, but it's very nice in most cases called train test split in sklearn. Basically, it's just using some random splitting. It will split your data into a training set and a testing set. In this case, I set the random state to 10, so it would always give the same random value just for the sake of reproducibility. But if you want it truly random, you can just remove that. Test size in this case is just this is just 20% of the data is going to be used for testing. You might want to have it higher or lower, but you probably don't want it to be 1. That'd be weird. But 0.15, 0.2, something along those ranges is generally pretty good. But it's made a test set. So on to the next part. We have, basically the rest of this is just kind of going through a series of different algorithms that are used for this type of thing. This is just type of classification. I start from logistic regression to kind of go down. They're all pretty similar, so I'm not going to go super in depth. I do mention a few of them that we haven't gone over. You can kind of go over them on your own if you'd like. So for instance, like k-neighbors, decision trees, and random forests are a few things that I did not go over that I'd highly recommend you guys go over if you are interested and have free time. But the main point of this is there's a number of different accuracies I have printed out here. I think the highest I got from this really simple version was like 81% or something. That's not super high, especially if you looked at the Kaggle competition, and you'll see some much higher percentages. So it's not great. There's a few ways of kind of going about this to make this a bit cleaner. As we've kind of alluded to already, we can make our features a bit better. So either remove bad features or make better features from what we have. The other thing that I've kind of glossed over is something called hyperparameterization. It's a long word, but it's really simple. Basically, it's just change parameter values for algorithms. So Let's see, what's a good example here? Yeah, this one. So for the k-neighbors classifier, you need to have, it's determined, basically, the really simplified k-neighbors is basically just seeing how similar all the, like how the other most similar entities to what you're currently looking at are to you. So for instance, if there's three rows that look really similar to what you have, you can kind of use that to make a guess as to what your value is going to be. But you can adjust what n neighbors is. I could make this be something like 2. I could have it be 100. That would be bad. Don't do 100. But you could mess with this a bit. There's a lot of different hyperparameters for each of these things. There's n neighbors. There's like the weights, least size. There's a lot you can do with each of these. But those things have the power to dramatically affect the overall strength of your program. There are a few things out there that kind of automate this process, but the consistency of which kind of varies. I would highly recommend you look into that if you want to go into this. Because this is such a simple data set and a small data set, this doesn't take long. I click on it, a second later it's done. You might not have the luxury for a larger data set or for anything more complicated. But yeah, that's basically it. Yes? For like the whole, from ML Mondays in general? Sure. So, I guess to go over the schedule again. Right, today we're doing tabular machine learning. This is, again, really simple related stuff. This is mainly just meant to get you an introduction. It is what's generally taught at the beginning. Next week we'll get into computer vision, which I personally find more interesting. Because you can do a lot. There's more. It's computer vision. There's more of a visual component to it. You can kind of see a bit more cleanly when your thing's working, how well it works, and it's kind of cool to see that. So highly recommend. Personally, have an interest of reinforcement learning as well, so do go to that one. I'll make sure to make that one good. But the main idea here is for this workshop. On the thing there should be a link to this. I think I've already opened it a couple times. But for this Kaggle thing, I basically just took the data off of this that is publicly accessible. There's also a test set on here that doesn't actually have the correct answers on it because, well, it's a competition. You're not supposed to know. If you knew, that'd be a bit stupid. But if you are genuinely interested, you could try to use this. So there's a lot of different processes you could go after to do this. If I recall, I said before how 100% accuracy is a bit cheap. I still don't like 100%, but wow, there's still a lot of 100% here. See if we can scroll down. Okay, yeah, we're getting to some 98s there. Obviously, this is a lot better than what I've gotten into on the worksheet. I think I got like 81%. So this is basically showing there is a major margin for improvement if you just look a bit more. So yeah, I guess I don't have a lot else to mention. Does anyone have any questions, thoughts about anything that I've presented up so far? That's gonna be a no. I don't have much else for you for today. I think that's, yeah, I guess you can mess with this more if you'd like. The workshop, the actual Google Collab is gonna be open for whoever wants it. There's some more in-depth stuff if you were to go to the Kaggle and go to code. I think if you go to, why isn't this loading? Oh, that's because I'm scrolled down. I think one of the best ones is probably the one with the most votes in this context. It's the one I showed you before. This goes into the data set in much more significant detail. Something like using some grids to figure out like the age distribution for survival, for instance, how it differs from not surviving. It could provide a lot of interesting context. But again, for brevity's sake, you can see how long this is. I obviously didn't go through all of it. Didn't go through everything. But there is a process here to look through. But if there aren't any questions left, then I think I will wrap it up, unless anyone has something else.
I have a question, actually.
Yes.
How would you go about like knowing which like regression or model to use? Like, you just test and see which one fits you the best?
A lot of it's just testing. Okay. There are you can kind of make some guesses. So for instance, a linear regression is probably not going to perform well if your data is very nonlinear. But generally speaking, it's hard to know until you do it. That's part of the downside of this type of machine learning. As I said before, there are ways to like automate the process on a bunch of different things. That's how hyperparameterization can work. But that is one of the downsides of this. You kind of just have to experiment at least a little bit. Yeah.
Is it recommended to just stick with the pre-trained pandas models instead of building it on by TensorFlow or PyTorch?
So I guess that's kind of a different deal. So this isn't going to relate to what I was talking about right now, but the idea is pre-trained models are generally pretty good at whatever they were pre-trained to do. That's important because let's just say your task is a bit different from that. Like if you're trying to, for instance, if there is some general pre-trained model, such as GPT-3, for instance, because that's pretty topical, it is trained on a huge set of data. But if you're trying to do something really specific on that, there's something you can do called transfer learning, which is basically taking that pre-trained model with all the sets in it and everything, and then just training it on your smaller data set for a little bit and kind of shortcut the results, because training on that big of a model takes a very long time, and it's great for someone like Microsoft to do most of the work for us. But does that answer your question, or is that? Okay, I guess it's a little bit more complicated than that. I would at least start from a pre-trained model and work your way from there, just because starting from nothing can be not amazing.
Yeah, like for this, would you think the leaderboarders just build their own models, or do you think they just make sure their features look very well done?
I'm honestly not 100% sure on that. I think chances are it's some level of mix. I will say, I personally, again, as I said before, I'm a little suspicious of the whole 100%, but because that screams overfitting to me. If you get like that kind of accuracy, chances are your model is learning how to do the same exact test really well. So if you get so imagine if like your students, you already know this. Imagine if you got the exact same test with the exact same questions like 5 times. Obviously, you would get pretty good at that test because it would just be the same every time. If you want your model to actually learn something, you have to mix it up, as long as they're like similar. But that's the idea. Any other questions before I wrap it up? All right, then I'm going to wrap it up. Just as a general reminder, week 8 is still a bit TBD. So if you guys have any thoughts about some topic of interest that really like speaks to you, please say something on Discord, and I will make a point of trying to get that on there. But with that, I think we can call it.
Thank you.